I'm going to talk about our blocking algorithm, which is what it does is it maximizes within every block the maximum gap between any two observations, right? But on some distance metric that I'm going to describe. It'll be any way you want to measure distance that you want, as long as it meets one very weak criterion. And what it does is that it minimizes the distance on covariate space in every block. Right? Now, this is a hard problem. Because as you get more and more data, this problem usually becomes an exponential problem, like it explodes. The combinations of all the possible ways of group my data, that explodes very quickly. So we have an algorithm that does it in polynomial time, which means that it's growing at a much lower rate. It's going to, the speed, the amount of computational time it's taking is not going, if n is your sample size, not going from something to the power of n, it's n to some polynomial. So it's very fast. It's by far the fastest blocking algorithm that has any kind of decent optimality. It works with any number of treatments, which most others don't, and you get to pick the minimum number of observations that are in a block, right? If you have 5 treatments, you can say in every block I have at least 5 observations. I'm going to tell you that's actually probably not a good idea to have as many observations in your blocks as you have treatments, because it induces some analytical problems. What you probably want is more observations in your blocks than you have treatments. But that's up to you to pick, and it will do it, right? And it gets really good balance because it's approximately optimal and well defined. And if you have more observations in there than you have treatment categories, you can calculate conditional variances, which I'll describe. Which if you didn't